The second significant figure rule that we need to know in Chemistry 11, and the one that we use most often in this course, is rule number 2, multiplication and division rule. In this rule, when we do our calculation, assuming that our operations are multiplication or division, our answer is going to contain the same number of sig figs as the data with the least number of sig figs in our question. So, in other words, we can only be as precise as the data that we use. So the values that we use to calculate, if we consider them, the one that has the least number of sig figs will determine how many sig figs we have in our answer. Let's do some examples of that. As a nice simple example, we've got 25.00 multiplied by 0.106. Okay, again, we can do the multiplication right away. It's going to come up to be 2.65. There's our answer. Let's look at how many sig figs we have in both of these values. Now, remember that when we're looking at our different values, we're going to have to remember those guidelines that we learned earlier so that we correctly identify how many sig figs we have. So, for example, trailing zeros where there is a decimal place are significant. So here we've got 4 sig figs. And in the second value, I have 1, 2, 3 sig figs. The 1, the 0, and the 6 are all significant. A leading 0 is not significant. This one does not count. So I'm allowed to have the least number of sig figs from my data, and therefore 3 sig figs is how many I'm allowed to have in my answer. So 3 significant figures is actually what I have, and I'm good to go. Let's do some more examples. Okay, here I have 0.401 divided by 72. Just bringing back some notation here from mathematics. Remember that when we have a fraction or we've got a line underneath the value, it's saying that it's being divided by another number. So this could also be written as 0.401 divided by 72, but it's not very often that we use, we set up a division in this way. We're more likely to use a line underneath the value that we're dividing. And so we'll get used to seeing that and recognizing that here. So 0.401 divided by 72, I've got, if I do that in my calculator, or you want to do some long division, we get 0.005569, value that comes out. Let's have a look at significant figures here. On the top of my numerator, I have 3 significant figures. The 4, the 0, and the 1 are all significant here. And on the bottom, I have only 2 digits, but they're both non-zero, and so they're both significant. I have 2 sig figs on the bottom, which means that I'm only allowed to have 2 significant figures in my answer. I must round my answer to have the least number of sig figs for my data, and so 2 is the answer. So here I can have to round my answer right here to the second 5. And I can draw a little line right there, okay, saying that the 6 and the 9 are not significant. I can't report them. But before I cross them out or get rid of them, I need to look at the digit after the 5, and I see that it is greater than 5. It's large enough to round up the 5, and so I'm going to report my answer as 0.0056, rounding up that 5. And there's my answer. I could also express this in scientific notation, which would be equally acceptable. And if I do that, I'm going to move this decimal place over 1, 2, 3 spots. And so I would report this number as 5.6 times 10 to the negative 3, because I've moved my decimal place over to the right. And in fact, this number is less than 1, and so I need to have a negative exponent. 5.6 times 10 to the negative 3. Both of those are acceptable, and they both contain 2 sig figs. Let's do another example. Here I've got 70 and I'm not going to use this x. I'm going to write this a little differently, just so we get used to different ways of expressing multiplication. So 70 multiplied by 62 is equal to, well, that comes out to be 4,340. But before I report that number, I need to look at my sig figs. In the first value, I have only one sig fig. Only this 7 is significant. Remember that a trailing 0 when there's no decimal place is not significant. So the number 70 really only has one sig fig. The second number, 62, has two sig figs. So my answer must contain only one significant figure. So that means I'm going to be rounding right here at the 4. I look to the 3. It's not great enough of a number to round up my 4, and so my answer is going to be reported as 4,000. 4,000 has only one sig fig, the 4 right here. Remember, these trailing zeros are not significant. It's also possible to report this in scientific notation. 4 times 10 to the power of 3 is also totally acceptable, and it also only has one sig fig. I'm going to do a couple more questions, or at least two more questions. One of them uses scientific notation, which we're going to see a lot of in this course, so we definitely want to be feeling comfortable with it. And I've got good news. When we're dealing with numbers that are expressed in scientific notation, in chemistry, when they're being multiplied or divided, the sig fig rule is actually a lot easier for multiplication and division. We simply look to the value, we ignore the power of 10, we ignore the exponent, we simply look at the value and we can count the sig figs just by looking at that. So 6.2 times 10 to the negative 3 multiplied by 7, let's say 7.5 times 10 to the negative 10. And what I mean, what I just said about ignoring the exponent, recall that when a number is in scientific notation, this is not significant. You do not include that power of 10 as part of the sig figs. So here I'm only looking at the 6 and the 2. I have two sig figs. And the same is true in the second number. I have two sig figs as well, the 7 and the 0.5. We do not take into account the power of 10. And the good news, unlike addition and subtraction, I'm not thinking at all about decimal places. It's just super easy. I've got two sig figs. I need to have two sig figs in my answer. So I can do that multiplication, and it will come out to be 4.464 times 10 to the negative 12. Sorry, 12. And I need to round my answer to have two sig figs, and so it's going to be right there at that second 4. And I look to the number after it before I go ahead and report 4.4. The digit after the 4 is a 6, and that is a big enough number to round up my 4. So my final answer is going to be 4.5 times 10 to the negative 12. And that answer has two sig figs. Great. Finally, I'd like to just do one more example that discusses counting numbers or defined numbers. You will notice in the course following this video that there's a note about counting numbers. And counting numbers are just essentially whole numbers. And they refer to things that you could count with counting numbers or whole numbers. So, for example, one dog. The 1 here is a counting number, and we can't have a fraction of a dog. So either we have any whole numbers would represent a dog. So we can have 0 dogs, 1 dog, 2 dogs, etc. But we can't have 1.6 dogs, hopefully. So 1 dog would be represented by a counting number. Another example might be 3 books. Later in chemistry, a great example could be in mole ratios, looking at a reaction 5 moles, for example. But we'll deal with those a little later when we get there. So counting numbers are any whole numbers that we can count. and they're used to express quantities that could only be counted in whole numbers. These don't count when we're looking at how many sig figs to have in our answer. Okay, so they don't count towards your sig figs. And by that I mean these are exempt from the sig fig rules. So if you have a counting number as part of your question, you can ignore it. Okay, you can, of course, you're going to include it in your calculation if it's part of it, but you don't need to consider it when you're asking yourself how many sig figs you're allowed to have in your answer. The other type of number that is exempt from the sig fig rules are defined numbers. And defined are often commonly called exact numbers. And what do I mean by that? Exact numbers or defined numbers refer to things that we know to be exact. So for example, 1 liter contains 1,000 milliliters. This is a conversion factor that we use in chemistry, and we consider this to be an exact conversion. In fact, many of our conversion factors are exact. Not all of them, but the majority of the ones that we're using in this course are exact. So 1 liter is equal to 1,000 milliliters would be an exact conversion factor. Another example would be 1,000 meters in a kilometer. So any of those SI conversions are, let me rephrase that, any of the conversions for SI units where we're converting from a base unit to another prefix would be considered exact conversions. So 1,000 meters is equal to 1 meter, also an exact conversion. So if you're using this conversion factor, both the kilometer and the 1,000 meters have only one sig fig, if you were to think of them as how many significant figures they have. But because they're exact, we could write 1.000000 kilometers because it's exactly 1 kilometer. So in other words, these ones, we simplify them by using whole numbers like 1 and 1,000 without any decimal places, but they are exact, and so they're exempt from the sig fig rules. Let me do an example of that. For example, let's say we were to measure a distance in meters, and we were to measure that it was equal to 6.24 meters. And we would like to know how many kilometers is that if we were to convert to kilometers. So you've done this already, unit conversions. You'd say, okay, what I want is the number of kilometers. It's equal to what I have, which is 6.24 meters. And I'm going to multiply it by what I know, and that's that conversion factor. 1,000 meters is equal to 1 kilometer. So I put my 1,000 meters in the denominator of my conversion factor, and my 1 kilometer would go on the top. And so I'm dividing 6.24 by 1,000. So I'm going to just essentially move that over 3 places. So I get 0.00624 kilometers. But when I look at my sig figs, I'm only considering the significant figures in my data, in the initial amount that I had, 6.24. Because the only other piece of information, the only other numbers that were used in this calculation were my conversion factor, and they don't count. This is an exact conversion, and we don't count it. So we would be allowed to have 3 sig figs, and this would be acceptable. And of course, we could change that and put it into scientific notation, and that would be fine too.